So welcome back, everybody. We are happy now to have Greg Bentsen from Brownian, who will talk to us about measurement-induced purification and large N. Please, Greg.
Okay, thank you very much. Thank you very much for the invitation to speak. It's great to see everybody again. It's exciting to be back at GeoFlow. So this is a project I've been working on for the last 8 or 9 months or so with Shubhayan Sahu and Brian Swingle. And we've been looking at measurement-induced purification in a new type of circuit, which we refer to as a hybrid Brownian circuit. So we've just posted this recently on arXiv. This is our post number there if you want to check it out. Okay, so I'm going to give you just a whirlwind tour to measurement-induced phase transitions because there's a lot in this field and I'm only going to cover a little teeny bit of it and I only have a limited amount of time. So the basic idea behind measurement-induced phase transitions is more or less that you have this competition between scrambling dynamics in a quantum circuit versus projective measurements. And suppose we have some quantum circuit made out of qubits and I just have some 2-qubit gates in a 1 + 1d circuit here. If I apply projective measurements only a little bit throughout this circuit, I'm going to mostly have a big unitary scrambling circuit and the input and output are going to be highly correlated with each other. But if I take the measurement rate to be very large, and by measurements, I mean these red dots or X's that I'm putting here, the measurements basically tear your circuit apart into pieces such that different portions of the input and output are no longer correlated with each other, or at most they're classically correlated. And just for people who have thought about this a lot already, notationally, I'm going to be using this parameter gamma to refer to the measurement rate. Now, a lot of times people use the notation P to refer to the measurement rate. So that's just something to keep in mind here. So this has been recognized as a phase transition as you tune the measurement rate up and down and you see your circuit kind of fall apart. Okay, now, like I said, this has become a very popular phase transition to study. There are a lot of different groups approaching it from a bunch of different angles. And this particular phase transition and cousins of this phase transition have been found in a bunch of different models. So it seems like this is a pretty robust phase transition that you can really find in a bunch of different places. Now, I don't have time to review all of the different areas where this comes up, and I'm going to focus on one, and that is in the context of purification. So if I have one of these circuits, and by the way, this was an idea that was originally proposed by Michael Gullens and David Hughes in this paper here. So if I have one of these circuits with unitary scrambling and some projective measurements, these red X's, one way I can probe this transition is to look at correlations between a highly entangled reference system, which I'm labeling R, and my system Q. And what happens is that as my measurements get really more and more, as I apply more and more measurements, my circuit gets ripped apart and the correlations between R and Q disappear. So that's what this plot is here. And one way to measure this phase transition, as was pointed out by these guys, is you can measure the entanglement entropy of Q. And if you're above the transition, meaning you have lots and lots of measurements, you destroy the entanglement, right? So my entanglement between these two things drops to 0. Whereas if I'm below the critical measurement rate, I can actually maintain some amount of coherent information between Q and R. And that's this red line here for exponentially long times. Okay, so this is just a review of what this purification transition is in the first place. And let me make sure I've got time in front of me so I keep on time. So this is the gizmo that we're going to be playing with. And this is the gizmo we're going to be using to probe this phase transition. And so we'll see this circuit come up a lot. And in particular, I'm going to introduce a new circuit that we're going to put in place of this blue guy here. So in this very rapidly growing field, there are still a number of big partially answered, some of them are partially answered, but some of them are still very open. Generally, we don't have a very good understanding yet of what are all the phases that are accessible in this competition between measurement and scrambling and all the different phase transitions. And one would like to, for instance, have a really organized classification of all the different universality classes that one might be able to see in these types of phase transitions and maybe compute GeoFlow and standard things like that. We would like to put this into a framework of phase transitions, just like we understand sort of typical phase transitions. And one part of that is to describe a field theory of this transition. And in particular, if we really believe that this is a critical point, then it ought to be described by some sort of conformal field theory. And that description is not yet clear. There are some other questions here, but in the interest of time, I'll keep moving on. So our main interest here is, or our motivation here is, can we describe these phase transitions using some sort of a field theory? And that's kind of our motivation here. So what I'm going to do is I'm going to introduce today a new set of circuits called hybrid Brownian circuits that makes this field theory picture particularly easy to get at. I'm not going to claim that we have a field theory, but writing down field theoretic descriptions of this transition are particularly easy in this formulation. So the first thing I'm going to do is just introduce what these hybrid Brownian circuits are, tell you about the ingredients that go into them, and I'm going to then show you how we can use these ingredients to derive a path integral expression for this phase transition. And so that'll be a field theoretic expression for this thing. Okay, and then in the second part of the talk, I'm going to show that these models have a large n limit. And I'm going to analyze this model in the large n limit and show you that using saddle point analysis, we can fully describe this phase diagram. And in particular, we can derive this expected time dependence of the entropy. Okay, and then I'll end with some outlook and future directions. Okay, so hybrid Brownian circuits. These are the things we're going to be working with. So I mentioned at the beginning that this phase transition is a competition between scrambling and measurement. And so we need kind of ingredients to represent both of these in the circuit. And the first thing that we're going to take in this circuit is the scrambling part. We're going to do that dynamics. We're going to use this well-known unitary Brownian spin dynamics introduced originally by Nima Lashkari and collaborators to describe fast scrambling. So this is a known fast scrambler, and it also has large n control, and you can also solve it in a couple of other ways using Ito calculus and things. But this is a nice known fast scrambler. And let me just point out a couple of features here. So this is an all-to-all spin model. So we have all-to-all interactions between spins, and the coefficient, the coupling between the spins, is going to be just Gaussian and Brownian. Okay, so this is an existing model. What we're going to do now is add in a second part, which is these Brownian weak measurement part. So this is the unitary dynamics, and we're going to add in this measurement part, which is non-unitary. And I don't have time to explain exactly what the measurement scheme is here, but you can basically think about it just like non-Hermitian evolution. So instead of this being an e to the minus h, e to the minus ih, excuse me, this is an exponential of some operator, e to the minus some operator. And this operator, in the simplest case, we're just going to take them to be single spin, sums over single spins, with these h coefficients here are going to be also Brownian random. Okay, and then what we're going to do then is just stack these two guys, alternating layers of these guys, and I'm going to call that whole stack V. That's going to be my circuit V.
I'm sorry, Greg, do you need a MT to be like smaller than 1?
Yeah, well, you need delta T. This is all going to be true in the limit of delta T is very, very small.
No, but O has it looks like the OT you have has eigenvalues that are positive or negative.
Yeah, that's true. Yeah, that's right. So what this guy is going to do, if you write this as an exponential, it's going to take whatever eigenvalues of O, and it's going to grow. Whoops. It's going to grow the highest eigenvalue of that and suppress the other.
Yeah, but I just mean like in measurements, you don't do that, right? It's always like a small, only shrinking.
Yeah, that's right. So it's not exactly the same as. I'm sorry, that's my dog. It's not exactly the same as measurement. That's right. So you should think of this more like a non-Hermitian evolution. So it's not exactly the same as a projective measurement.
Yeah, measurement should have some kind of nonlinearity here, right? You need to some dependence on the state, right? That's not here.
Yeah, that's right. And sorry, I really should be writing an approximate here. Yeah. So okay, let me actually let me tell you what the measurement actually is, because this is a good question. And I put this on my backup slides, but let me just go through the end and show you what the measurement actually is. Okay, so this is what M actually is. So what we do is we take the whole system and we couple it to an auxiliary qubit, and this is initialized in a 0 state. And we couple this thing using this operator O, times just the Pauli X operator. So this is some unitary interaction between these two, and then we just do a projective measurement on the Y basis of this auxiliary qubit. So it is, and when I write this all out and I ignore the qubit, I can write it in the form I said earlier, when delta t is very, very small. So there is a Born rule here.
But there is still a nonlinearity. You still, then you have to keep the qubit somehow, right? So qubit degree of freedom and never trace it out. Otherwise, it's not measurement really. So.
Well, I mean, this whole channel doesn't need to have any nonlinearity.
Yeah, the channel doesn't need, but then you have to keep the qubit.
Yeah. So one way you can think of this is that I've done a let's say I take this to be a non-destructive measurement. So the qubit sticks around, and now it's in the eigenvalue of y plus 1.
Right, but then you have to measure not entanglement entropy of the system, but conditional entanglement entropy conditioned upon the qubit.
Yeah, that's right. So, if that's the point, then indeed. So that's exactly what we're doing. Every time we do one of these measurements, we're going to post-select on a +1.
Okay. Always +1.
Always +1.
That's forced measurement. So there is no Born rule here.
Yes, that's right. Exactly. Okay, so yes, exactly. We're doing forced measurement.
It might be a different universality class though. But
that's right.
Yeah.
Absolutely right. Yep. Exactly. One of the things that we talk about later in the paper is whether you can actually access other universality classes because by averaging over non-post-selected measurements. But for the moment, I'm just going to say post-selected. Right. So, and generally there is this question of, if you don't post-select on measurements, there's this question about whether you're in a different phase transition, which folks call the measurement phase transition, if you don't post-select, or the forced measurement phase transition, if you post-select on these outcomes. But what we're going to do here is we're just going to, we're going to post-select on a particular outcome. So every time we do one of these measurements, it's going to be just a +1. Yeah. Okay. So good. Thanks for that. Okay, so when we do that, and when we apply these this M gate, and we post-select on that measurement, we get this operator M, and when we stack a bunch of these in a row, we get this operator V. And so I'm going to then stick this circuit, this operator V, into my purification circuit, and then we're going to see by measuring the entanglement entropy of Q here, we're going to see as a function of this measurement rate gamma, whether these two guys stay entangled or not. And so this whole model can be parameterized in terms of just 3 parameters. We have gamma, the measurement rate, T, the time, the total time that the circuit acts, and this other parameter K, which I'll hopefully come back to later. K just refers to the size of some subregion A here. Okay, so our order parameter here is just going to be the purity of the state rho squared, or I can take the logarithm of that to get an entropy. Okay, so we're going to talk about disorder average in a second. I know that's what people are thinking about, but let me just say first, so the goal here is going to be to compute a path integral expression for the purity of the state Q. And if I write that down in a sort of a tensor network picture or a circuit picture, it looks like this. And I'm going to call this thing Z2. So let me not go ahead yet. Okay, so here we have 2 density matrices here and here, and each of them is acted on by, here I've got the ket part being acted on by a V, and the bra part is being acted on by a V dagger. And in order to get this rho squared, I throw in a swap, I do a swap test, and I do 2 identical operators, rho and rho prime, and I put a swap operator at the end. That's what this orange guy is here. And by taking the trace of that, then I get the purity. Okay, so in here I have 4 replicas total, and I'm labeling replicas by the number of V circuits I have. And I'm not going to go through the details here, but using some circuit identities, more formally the Choi-Jamie-Opowski isomorphism, you can turn these dynamics on 2 density matrices into a pure state dynamics on 4 pure state replicas. And this is a standard trick that lots of folks have used in this field to turn this mixed state dynamics into 4 replicated pure state dynamics. And as you do this, you see that some of these circuits come in with a V and a V star. And that's coming from this identity here where you have a V adjoint, and you're going to pull this over through the EPR pair, and it shows up here. Now, the thing that I want to point out here is that the swap operator gives you different boundary conditions at the initial time and the final time. So here at the initial time, we have replicas 1 and 2 that are correlated with each other. Yep. Was there a question?
Functions of it, PFM and theta.
I'm sorry, I can't hear you. Okay, maybe I'll continue. Sorry if there was.
Maybe we can type. Whoever was asking the question could maybe type it into the chat.
Yeah, it may be just someone forgot to mute the mic, because I saw someone just muted it.
Okay, well, so I'll continue. Okay, so we have the circuit on 4 replicas, and the goal now is going to be to write this whole thing in the path integral formalism. But before I do that, I want to take some time to talk about disorder averaging, because that's an important aspect of this. So the goal is we're gonna take this circuit, and the way we're going to turn this into a path integral is we're going to take all these different layers, each of which has these Brownian coefficients in them, and we're going to take a disorder average, and that's the thing that's going to make this thing tractable. Now, in order to take a disorder average, so naively, I'll take this quantity Z2 and just take a disorder average over it. But I told you already that V is not unitary. And this is the point that Xiaoliang and Ehud were pointing out, is that there's this post-selection. So I'm actually reducing the size of the state every time I do a measurement. And I need to take that into account if I'm going to do the proper disorder average. So really what I'd like to compute, what I ought to compute, is this Z2 divided by P squared. So I need to normalize by the Born probability, where P is just equal to the trace of the state. Okay, now this is just difficult to compute, and this has been pointed out by many people in previous works on this. And instead, what is a common technique to make analytical progress is to compute instead the ratio of the averages here. And that's what we're going to do here. And we show in our work here that both of these are sensitive to the transition. And we show actually in an appendix that these actually require equivalent quantum resources in order to simulate some sort of an actual experiment. And we've done some ED numerics that show that actually these two quantities look like they're almost equal deep in the mixed phase. And so this is something that we need to understand a lot more. And just to point out here, the ultimate goal is going to be to what we really want to do is compute the average over an entropy S. And this is actually putting the disorder average outside of the logarithm. Okay, and now we have to use these tricks where we do a replica limit to use these averages in the right way. I'm not going to worry about these things yet. We're still early days with this model. So for the moment, I'm going to just content myself with computing this disorder of averages. Okay, and just to say what I said again, we're going to put this Z2 quantity up here. We're going to average over our different disorder quantities. Here, green again is the unitary part and blue is the measurement part. And we're going to divide by the squared probability. And just to point out here, the difference between these two guys is the Z2 has these boundary conditions between 1 and 2, but because of the swap operator, you get this different boundary condition between 1 and 4 and 2 and 3, whereas P squared has the trivial boundary conditions on both. And we're going to compute the disorder average of these guys and take the ratio. And that thing I'm going to call a quote unquote purity, because it's not actually a purity. Okay, maybe I'll just pause there for a second for questions. Does this make sense so far, or are there other questions? Okay, great. All right, now I don't have the time to actually explain the calculation of how this turns into a path integral, so I'm just going to kind of explain intuitively how it happens. But this is a familiar story if you've worked with any sort of disorder average in a spin glass type of calculation. And what you get is if you average over the disorder coefficients, J, and also the other measurement coefficients, you're going to trade these couplings in SI, SJ for couplings between replicas, SR and SS. So the picture you should have in mind now is I've got these 4 replicas, 1, 2, 3, 4, where each of these is a V or a V star. And what I'm going to get actually are couplings between spins that reside on each of these different couplings. And this is, again, a pretty classic story that comes up in spin glasses. It comes up in other works on these measurement-induced phase transitions. And what we're going to do is capture these correlations between these 2 replicas by these mean fields G. And these mean fields are simply just spin-spin correlations between replicas. Importantly, though, because this is because this has a large n limit, this mean field is a uniform sum over all of the s.s terms, in a sum over all sites I. And so what that means is you get this nice 1 over n factor in front. So each of these spin-spin correlation things is a classical field controlled by 1 over n. And that's kind of the magic that makes this model tractable. Okay, so when we do this disorder average, I'm just going to flash up the full expression that we get. So this is the path integral expression that you get for the disorder averaged Z2. And I'll kind of lead you through bits and pieces of this. So first of all, these G fields, GRS, are the fields that I've just introduced before. So these are just the mean field coupling fields between the 2 replicas. This F field is just a Lagrange multiplier. So we want to enforce the condition. We want to enforce this condition right here, that G is actually equal to these s.s terms. So that F is just a Lagrange multiplier. And then the actual spin dynamics is contained in this propagator K, which I've written down here. Okay, so let me point out a couple of other things too. So in this first term, this part is coming from the unitary part. So this is a J controlled by the J unitary scrambling part. And we've got another term here coming from the measurement part with a gamma. And then we've got this Lagrange multiplier term, and then we've got the spins. And in particular, the boundary conditions that I mentioned earlier, where we have these 1 to 2 boundary condition, and then 3 to 4. And then at the end, we have a swapped boundary condition. These are taken into account by these states, psi0 and psi t. Okay, and so in particular, this propagator is actually, we're talking about the dynamics of taking some system of 4 spins from a particular state, psi0, to a different state, psi t. And the fact that the swap operator is in there means that psi0 and psi t are different, and that's going to be really important in the physics. Okay, now another piece that comes into this is this whole system is actually SU2 symmetric. The bulk physics is actually SU2 symmetric, and that leads to a great deal of simplification in this problem. So instead of having this big, oops, I can't go backwards. There we go. So I started out with this big, large N path integral expression, but because of the SU2 symmetry, many of these fields just drop right out. And the only thing I actually end up with is a single effective spin 1/2, which I call psi. We call this an R bit or replica bit. And this psi is just a spin 1/2, and it starts in this state, psi0, and it propagates through to a different state here. And the 2 states that I propagate between are actually spin singlet states. So at the beginning, here I start out with replicas 1 and 2 maximally entangled, and replicas 3 and 4 maximally entangled. I can think of that actually as just spin singlets between 1 and 2 and 3 and 4. And then at the end, that's actually not exactly correct. I'm sweeping a little bit under the rug there, which I'm happy to talk about. Up on the top, now I've almost got spin singlets between 1 and 4 and 2 and 3. Okay, so that's what these red lines here are. And so the whole dynamics here just happens in the space of total S being 0. So S total being 0, where S total is the sum of the spin over all 4 replicas. Okay, so what I have in the end then is a large N path integral expression for Z2. And in fact, I also have a path integral expression for P squared. It's exactly the same path integral expression, except that now my states are the same at the beginning and at the end, because P squared just doesn't have the swap operator. Okay, so that was an introduction to our circuit. Now I realize I'm running short on time, so let me get to the interesting physics that comes out of this large N path integral. So this is the spin 1/2 path integral that I wrote down before. And all I'm going to do now is just analyze it in the large N limit. So let me just back up here. So this is I told you that this is our spin 1/2 path integral that describes the purity. Okay, and it has a large N limit. And if we just look at this action, we just take this action as a function of its fields and just plot it, we see that above the critical measurement rate, it's got this nice quadratic form, and then below the critical measurement rate, it splits into this double well potential. So all I'm doing here is plotting this I as a function of these fields B, and we see this nice Z2 symmetry breaking transition as a function of the measurement rate gamma. And this bulk symmetry breaking is really what's responsible for the measurement-induced phase transition. Okay, now because of these non-equal boundary conditions, right? I've got this propagator that goes between psi 0 and psi t. This time-independent saddle point where I just sit at the minimum can't be the only story. I've got to start in a state that's very close to my initial condition. And then I probably want to spend all of my time in this potential minimum, but then I've got to end at my other final state. So there's going to be some time-dependent configuration that dominates this saddle point. And likewise, below the transition, when I have these two distinct minima, I'm going to have to traverse between those two. So I've actually almost got it's equivalent to a tunneling physics in a double well potential. Okay, let's talk about that a little bit more. So what I'm going to do here is take these plots of my potential, and I'm just going to put them on their sides. And what I'm drawing here is my fields Bx, and this is what we expect to happen. So I'm going to start near one boundary condition, and I'm plotting time along the x-axis. So I'm going to start along one boundary condition, go to my saddle point, and then hit my other boundary condition here. So that's what Z2 is going to look like above the transition. Below the transition, though, I've got these two different saddle points. And what happens there is it's best for the system to sit on one of those saddle points and then transition to the other saddle point, and then finally hit its boundary condition down here. And this transition in between the two is called an instanton. This is whenever you have two degenerate or nearly degenerate minima in a potential, especially if you have different boundary conditions, you can drive these instanton transitions between these two potential minima. And in particular, the cool thing about this instanton is that there's, to lowest order in t, when you take time to be very long, there's a zero mode motion of this thing. So this instanton can happen at almost any time in the bulk, except for very close to the edges. And so what you get here is you get a contribution from the instanton where you get an exponential sort of action and an energy cost to this instanton that depends on the action it takes you to go through these, to actually traverse. But in addition, you get this entropy, and this entropy comes from the zero mode motion of this instanton that can be anywhere in the bulk. Okay, and this is exactly what you need to explain the phase diagram of measurement-induced phase transition. So that's, or at least in the purification setup. So that's really nice. And let me just explain exactly where that comes from. And let me ask, how much time do I have? Because I want to make sure I don't take up too much.
About 15 minutes.
Okay, great. Okay. Okay, so this is the case for Z2. And remember, to compute my purity, or my quote unquote purity, I need to take the ratio of my average of my Z2 divided by P squared. So let's see what happens with P squared. Now P squared, let me remind you, Z2 has different boundary conditions at the initial and final times, but P squared has the same conditions at the initial and final times. Okay, so these pictures now for the time-dependent saddle points for p squared, I've got to go from my initial condition at psi 0 down to my saddle point, and then I've got to go right back up to my same boundary condition again. And that happens above the transition point and below the transition point. So here I've got one, below the transition point, I've just got my one saddle and it goes between the two. Here I've got my two saddles, but one of my boundary conditions is much, much closer to one of the saddle points than the other one. So the other saddle point here doesn't even come into the computation for p squared. So we get these two very different behaviors for Z2 and p squared. For Z2, below the transition, we get this instanton action, and that is forced by this non-equal boundary condition. Whereas when p squared does not have an instanton. So when I just take the ratio of these two, and here I'm just going to argue just sort of heuristically and in a cartoon picture here, it gives the right answer. You can see that if I take the Z2 divided by p squared, you can see that the contributions coming from the saddle point are the same in both of these. Those guys are going to cancel. The initial time dependence is also going to cancel. Those are the same. And in fact, you can argue to yourself that this time dependence and this time dependence are also just symmetric about bx. So everything's the same. And so when you take the ratio of these two things, you get approximately 1. Now, by contrast, below the critical point, these two behaviors are very, very different. And when I divide these two things, again, you can convince yourself this thing is the same as that, and this guy here is roughly the same as that. And so the only difference to lowest order is this instanton contribution. And you get that action cost, and you also get a time dependence from the zero mode motion. All right, so then if I want to, let's just take the negative logarithm of this so it's easier to plot. Okay, so the 1 turns into a 0, and I just take the logarithm of this right-hand side. And that gives me exactly this phase diagram that I was looking for in the first place. Okay, so let me just to kind of repeat, within this large N hybrid Brownian model, we can analytically get a prediction for the purity of the system. And in particular, above the transition point, the quote unquote entropy drops to 0 very quickly, whereas below the phase transition point, you get this macroscopic entropy that sticks around for a very long time. And actually this log entropy gives us a clue about what happens at very long times. So you can now imagine what happens when I take t to be, what happens when t is exponentially large in n. Then these two terms become comparable, right? And that actually refers to the end fate of this phase that in the middle of this phase, I have just one instanton, and that's what gives me this log term. When I get to very, very long times, I get instanton proliferation. I just get lots and lots of instantons, and they just destroy the phase. Okay, now you could be looking at all of this and saying, well, this looks a lot like a Z2 symmetry breaking Ising model. And if you said that, you'd be absolutely right. This whole thing is completely described by a 0 plus 1D classical Ising model. And in fact, we can write down an exact field theory from this, starting from this large N path integral expression. We can take near the critical point, we can take this value, the field Bx is very, very small. And just in this cartoon picture here, you can imagine that these two, saddle point minima are at close to the transition. They start to approach each other, and so you have the symmetry breaking is very small. So we can use Bx as a small parameter and just expand the entire path integral around that. And when we do that, when we fix this other field Bz and expand around in Bx, we get exactly a phi to the 4 theory in Bx. And this mass in particular is set just by the difference between the measurement rate from the critical measurement rate. Okay, so this is exactly just a 0 plus 1D Ising model. And in particular, this, this kind of physics of the breakdown of the phase at late times is exactly what you'd expect if you had a 0 plus 1D Ising chain with different boundary conditions at the end. You have domain walls in between. If you make this chain very, very long, you're just going to get a bunch of different domain walls. Okay. Right. So all of this is just a 0 plus 1D Ising model. And in particular, okay, so we can compute the critical exponents from this thing. And I just want to show you this. If we plug this large N path integral into, and we solve the, if we try to find the minimal action using gradient descent, we find the same critical exponents. Okay, so that's just to say that these sort of nice analytical arguments are also backed up by some numerics. And let me just pause there for questions, actually, because the next thing is going to be a slightly different thing. So the big takeaway at this point is that we have a large N path integral expression for this particular quantity, this particular purity quantity, and we can write down a field theory for this transition, and it looks exactly like an Ising model. So that's the takeaway for the moment. And let me just pause there before I go on to the last little bit of the talk.
So the p square, can you calculate p fluctuation of p, which means p square minus the average value of p square?
Yeah, we could compute that.
Is that small in this limit?
Yeah, you want to say the fluctuations of the probability, or?
Yeah, I mean, if it's small, then it makes sense to at the beginning you have that approximation. So
yeah, exactly right. You want to say that on any particular disorder average realization,
yeah,
p is basically the same every time. Yeah, that's right. So that's something we haven't. Well, okay, we've checked this numerically, and it does look like. Let me say what I do know. When we compute Z2, when we compute the ratio of the disorder averages, and then we compute the disorder average of the ratios. When we compute those in exact diagonalization for n equals 6, those two things look almost the same deep in the mixed space. So I would be very unsurprised if your statement was true. I do expect that the variance is small. Yeah, it's something we should just check because it is readily calculable.
Just a very naive question, like this transition is equivalent to a 1D Ising model, but we know that 1D Ising does not have a phase transition. Right?
Yeah, right. That's a great point. So, and the transition I'm talking about here is different. So right, the statement there is just that if you have a 1D Ising, classical Ising model, and the temperature is your parameter, then indeed, if you take the temperature, yeah, there's no phase transition at finite temperature there. This is different though, because we're not talking about a classical statistical system at thermal equilibrium. Here, what we're talking about is we're putting this thing between two different boundary conditions, and the probe of this is now an entropy quantity. So it's a completely different. Yeah, I'm not explaining this particularly well, but the mapping to temperature is not a, it's not a relevant thing here. So yeah, so you're totally right that yeah, there's this lore that classical Ising model in 1D has no phase transition. That's completely true. Here we're just talking about the same microscopic model, but it has a completely different origin.
Right. But I'm thinking that like this n, this large n, I should think of this n as kind of temperature, right? Like if n goes to infinity, looks like temperature goes to 0.
Yeah,
like,
yeah. I
like
see.
you are working with large n, meaning that you are working with a classical, like a mean field theory, right? So, and in mean field theory, the Ising model always have a phase transition.
Yeah, that's right.
Right, and I think yeah, that mean field transition is exactly what you are talking about, right? So
yeah.
But like if you have finite n, or like this n is not infinite, then like there's no other parameter in the Ising, in the 0 plus 1D Ising. So
yeah, okay, so that actually makes it easier for me to give you an answer. So right, right, the standard lore is that when you take an Ising model and you take the length of that chain to be infinite, right? We're taking the thermodynamic limit. In that case, there's no transition, and that the reason for that is precisely this argument of kink wall, domain wall proliferation. right? So exactly. So in the thermodynamic limit of an icing chain, you get no phase because it's just broken up by icing by kinks. So that's exactly what's happening at late times here. That's exactly this phase, or part of the phase diagram. Now here, when I say that there is a phase in your picture of the Ising model, that would correspond to a finite size Ising model. Right. And in that case, you could say that there is, okay, right. You know, that's the sense in which there's a phase transition, is that we say that we're taking a finite size Ising model.
Sorry, but it's zero plus 1, right? You have a finite size Ising, still, there's still not a phase transition, right?
Yeah, right. So
I think it's the large n limit, right? In the large n limit, there is a transition. It's just not, you can't think of it as 0 plus, well, you can think about it as 0 plus 1 dimensional, but it's not the 0 plus 1 dimensional Ising model. It's just the 0 plus 1 dimensional mean field model, and it has a mean field transition. When you go beyond a time that is order n or something like that, then you go beyond the mean field. Then you have to go beyond this mean field, and these fluctuations cause the phase to decay. So that's why you don't have long-range order, true long-range order beyond this scale of, maybe here it's exponentially long in n, but
right, exactly.
But it's basically beyond that time scale. The large n theory is not, or the large n mean field saddle point is not exactly correct.
Yes, exactly. That's another way of putting it. Right, exactly. Is that this configuration with many instantons in it is not an exact saddle point solution. It's some approximate saddle point. So you should think of this as like a subdominant saddle, and I need to add this in only at finite n. So at finite n, this will be some like 1 over n subdominant saddle. So
the correct way to view it is as an infinite dimensional Ising model before you reach that time scale. And in this infinite dimensional model, of course, you have a phase transition, but beyond that time scale, one of the dimensions, the time dimension, becomes much longer than all the other dimensions. And
right.
In that case, you're really in a one-dimensional system.
Okay, that's a nice way of putting it. Yes, I see.
Oh, sure. Yeah, that makes sense.
Uh-huh. Okay, great. Thanks for that. I like that. Yeah. Okay, any other questions? Thanks for this, by the way.
There are 2 minutes left.
Yeah, maybe actually, let me just advertise quickly that there are some connections here to quantum error correction. And maybe if people are interested in talking about that, maybe we can talk about it. But let me, I do want to leave some time for questions. So let me just kind of summarize, and I can just be done. Okay, so there are a lot of different models where this measurement-induced phase transition comes up. And here, what I've introduced today is another platform for getting analytical results in certain cases. And this is, I consider this to be very complementary to existing technology, and might just give us some new handles, some new analytical handles. And in particular, we get a path integral that's tractable at large n. And one thing I really want to stress a lot is today I just talked about, and we've understood the purity case, meaning Renyi-2 entropy. But what we're really interested in is going to higher Renyi entropies. And we believe that that's to some extent possible in this model. And that's kind of work that we're moving towards right now. Right, so future work is to extend this to higher Renyi entropies, put this models like this on chains and lattices, and maybe get some critical exponents, you know, in the x direction. Look at 1 over n corrections, think about other degrees of freedom, and possibly think about taking a replica limit so that we can possibly start working towards a conformal field theory. Okay, so that's kind of my summary. Let me stop there. So thanks very much, and I'm happy to take some questions.
Good, so let's thank Greg for the very nice talk. We have time for maybe one more question.
Could I ask a question quickly? The diagram which had the sort of instanton, you had sort of kink and anti-kink. Could you? Yeah, here 3. So could you perhaps describe a little more what's going on in that configuration?
Yeah, great.
What sets the scale of the plateaus between the instantons?
So right, the size between these two saddle points.
Oh yeah, that part I get. No, the
that's
actual
fine.
The plateau part, the wavelength part. Because this is
size of the instanton.
Because these are tangent profiles which are connected, and the interval or the plateau over which they connect. What sets the scale?
That is set by the mass. So that's set exactly by this guy here. So if you take this phi to the 4 theory, that's what's describing this potential here. And you can imagine if I take this m to be very, very small, then the instanton, well, there is no instanton. It just goes straight from one to the other. And that's still true mostly when this guy is small. When I take these saddle points to be farther apart, meaning that I have a big mass, this instanton now takes a longer amount of time to get over. And so the time scale is actually set by the mass here.
So maybe I was misinterpreting the figure. I thought that the transition layers, that was the instanton zoomed in.
Yeah, I'm not sure I understand. Yes, it is.
So as I'm saying, so you have an instanton transition from one level to another, and then a sort of an anti-instanton coming back.
That's right.
And what I was interested in is the distance between the instantons.
I see your question. Okay, this m, I thought you were asking about what the time scale of the actual.
Oh no, that part I see. No.
Okay, so that time scale is set by m. Okay, your question is much more interesting though.
Thank you.
This time scale is not set by anything. These instantons are free to move. So this guy, as long as, so this is what's called a dilute gas approximation when you deal with instantons in the path integral. And at very, very long times, what I'm assuming is that the distance between these instantons, which is what you're asking about, is much longer than the actual tangent time. But because of this zero mode motion, these instantons can be wherever they like. Right now, if they come too close together, there's going to be a penalty in the action. Right, and it doesn't like that.
Sorry, if I may comment, I think that length scale, which is the average distance between instantons, is determined by inverse of the density of instanton, which is exponentially long because the instanton has an energy that's high, right? Yes, that's right. But even in any one of these configurations, so that's right. So, but in any one of these configurations, these instantons can move around, right? For any one configuration that I have, just an average.
Yeah, that's right. And then you can say within that ensemble, what's the average, right? And that is set by the cost of the instanton, the energy cost, which is here. So that's a ratio of the energy costs relative to the amount of time that you have for these instantons to be there.
Okay.
Yeah. So yeah. Sorry, I didn't.
No, that's fine. I'm sort of mapping it in my mind to another class of problems, which is spin ordering dynamics. So that was the picture I had in mind. So I was actually trying to work out whether or not there was a dynamics associated with the instanton interactions that you could map out as well.
Yeah, I expect that there is, because this picture is a really naive dilute gas approximation where I've said everything's very far apart. But exactly, I do expect that when the instantons get close to each other, there are interactions between them, and that leads to some other subdominant effect that I have not at all discussed here.
Yeah, thank you.
Yeah.
Good. So let's thank Greg again.